Hey, sorry, it was a bit of an emergency break as my dog has been barking at something outside. Um, okay, so I'm going to modify this slide a little bit, so the version you'll have will be slightly different from this one. What is important to consider is that the probability to get a C after a long period of time does not depend on the original nucleotide. Okay, it would be the same if I replace this with a G, or this with a T, or this with a C even. You would have the very same right-hand side to this equation, and this pi of C depends only on C. Okay, so it means that you have an horizon distribution, meaning that if evolution takes place over a very long branch, what you see at the end of that branch is the set of 4 probabilities corresponding to the equilibrium distribution, or stationary distribution, pi subscript A, pi subscript C, pi subscript G, and pi subscript T. Okay, these 4 depend on the model itself, and they exist if the model is called stationary. Most of the models we use have this property of stationarity. Time reversibility now is basically this fact, the fact that, or the property that when you have on one end of a branch an A, and on the other end of that same branch a C, you don't know. Your model doesn't help you understand whether time occurred from left to right or from right to left. These are simple models in themselves, okay? Just one branch with 2 tips is a model of evolution, is a basic tree, okay? We can calculate the probability of this tree. The whole probability of this tree is to have A at the beginning. So this is the a priori probability, probability to have A at the beginning of the branch, and then probability that this A evolved into a C over a time t, or a branch length t. Okay? So this writes this way: probability of A times probability that this A evolved into a C. Okay? So that's probability to have an A and probability to get a C after a time t. Here, this model is the probability of this evolutionary tree is the a priori probability to have a C multiplied by the probability of transition from a C to an A over time t. By the way, when we write this probability over time t to have a C transformed into an A, it doesn't say anything about what's happening here. This in no way says that there has been along this branch only one substitution event, right? Not at all. It just says, okay, probability to have the A at the end of a branch of length t, where at the beginning I had C. Okay, you may have many evolutionary events along this branch. This probability only tells you about what's the probability to have finally an A after a time t of evolution from a C. In time reversible models, these 2 probabilities for a tree are the same. Okay, this is a minimal tree, but this is a tree with 2 nodes and 1 edge. This tree here has same probability as this tree. In other terms, there is no preference for the arrow of time to go from left to right or from right to left. So time reversible models do not give you any indication about the orientation of the time arrow. Okay, so as a consequence, time reversible models cannot lead by themselves to a rooted tree. You cannot get a rooted tree by just using time reversible models. We'll use techniques to root a tree, but when you see an unrooted tree, wherever you would place the root, it would not affect the probability of that whole tree under a time reversible model. Okay? Exchangeability rates. Okay, so you'll see, this is a bit technical, but sometimes you will see that a model is expressed in terms of exchangeability rates. When this model is time reversible, what we have is this, and the probability to have A a priori will be the equilibrium probability of A. Okay, so we rewrite this like that. Equilibrium probability of A, that's the probability of A a priori without any information, any additional information. I give you a point in the tree, I say without any other information, you don't know where is this point in the tree, what's the probability to have A, that's the a priori probability of A, and that's the equilibrium probability of A. So it assumes that the model is stationary. So we rewrite it like this. PA probability over time t to have A to C is equal to pi C probability to have from C to A over time t. Okay, and using instantaneous rates, if we say this t becomes tends to become is so close to zero, okay, tends to zero, we transform this into the instantaneous rate of transition from A to C. And here we transform this into the instantaneous rate of transition from C to A. And we'll see these instantaneous rates appear in transition matrices. And these transition matrices describe the evolutionary model. So here we have this equality, pi A times the instantaneous rate of transition from A to C is equal to pi C times the instantaneous transition rate from C to A. So we can define symmetric exchangeabilities. If you have the ratio QAC divided by pi over C, this one put it there at the denominator, this one put it there at the denominator, and you have equality. So you have equality between this and that, okay? So you see that it's symmetric in the two characters A and C, okay? If here in this expression you replace A by C and C by A, you have QCA divided by pi A. Okay, that's it. So it makes sense to say, okay, we have an interesting equality that is symmetric. So let's give a value to this, and let's call it exchangeabilities. And the exchangeabilities, of course, are symmetric. That's the purpose of using exchangeabilities. The exchangeability here can be written SAC, and this is SCA. It is the same exchangeability. It's the same value. Okay. So it reduces the amount of information you have to give in order to describe a model. Instead of having to give the 16 instantaneous rates, if you think about a matrix 4 by 4 that will describe our model, instead of having to give the 16 QAC, QCA, QAG, QGA, QTC, QTG, QGT, etc., etc., all these 16, instead of this, you can give the exchangeabilities. How many are they? Much fewer. You have the exchangeability between A and C, between A and G, between A and T, and then between C and G, between C and T, and finally between G and T. You have 6 of them. Okay, you give these exchangeabilities and you give the 4 equilibrium probabilities. So instead of having to give 16 parameters, you can give only 10 to describe your model. And we'll see that in fact you can give fewer than this. But, okay, so just remember that when we have a model that is at the same time stationary and time reversible, very commonly this model is expressed in terms of exchangeability rates. So just know that from the exchangeability rates, you can go back to the instantaneous transition rates as long as you know the background probabilities. We also call these background probabilities or equilibrium probabilities. These are our stationary probabilities. Okay, let's have a break now before we talk about the JC64 model.